Hello guys, this is 11.3. We're looking at polar coordinates. So, um, before we get started, I just want to go back to simple algebra for a second. Let's say I have the xy plane, right? And then we have a point on the xy plane, point A, with the coordinates 5, 3. So, what the coordinate is telling us is in order to travel to this point from the origin, we have to travel 5 units to the right, right? Five to the right, and then three up. Right? That's what the values are telling us, right? Of the x value and the y value that tell us which direction we have to travel in order to get to that point. Now, polar coordinates is another system that allows us to get to this point, A, without doing traveling to the right by 5 and then up by 3. What we're going to do is we are just going to go straight from the origin to this point. Oops, that's not straight, right? Like that. Okay. So the idea of polar coordinates, I'm going to write it now first. So polar has two parameters, r and theta. And we're going to talk about that in a second. Let's go back to this xy plane for a second with the 0.53. All right, so five to the right and three up. Now, what this line that directly connects the origin and the point, this is gonna call r, right? That r is going to be the distance from the origin to the point, right? So you can think about this as the hypotenuse of the right triangle, or kind of like the radius of the circle, right? And that's actually how we pick this symbol r, or the variable r, to represent this distance, right? Because it works like the radius of a circle, right? If you think about the unit circle, we use r to represent the radius, right? So first we need the distance of this line, and from trigonometry, we are able to figure out what this angle is, right? This angle theta, right? By using sine, cosine, simple um, trig functions to find out what theta is, right? And that these two values, r and theta, they are our parameters for polar coordinates. In simple words, another way to get to this point, A, is first we need to figure out the length of the line we're going to take, right? In this case, radius, right? How long of a line are we going to take, right? And once we have decided on that, the next thing we need to decide is what's the angle of rotation, right? How much do we rotate this r to get to some other point, right? And this point that we rotated the r by angle theta is going to have the coordinates r and theta, right? Now let's take a look at some example. Right? Let's say I want to plot um, p of 2 and pi over 6. Okay. So what this is telling us is we want to take the radius of 2 and rotate it by pi over 6. Right? And let's try that. Now this is actually pretty hard to graph by hand, but you'll get the idea. Let's say 1 and 2. Okay, 1 and 2. I'm going to take this line and rotate that by pi over 6. So pi over 6, that's 30 degrees. That's about, I'm just going to give it a rough sketch like that. Oops, that's a little too much. Let's say it like that. Okay, and then we will get this new line. Right? And this new line will have the same length, which is 2, but it's now rotated by pi over 6. So this point that we have on the end of the line is going to have the polar coordinate of 2 and pi over 6. Okay, so polar coordinate is just another way to plot points on the xy plane. Okay, so let's talk a little bit about these two parameters, r and theta. Right, r is going to be the distance from the origin to the point, right, where the origin is the same thing, and theta is the angle from initial ray to OP. Right, so the green line will be our initial rate, and the orange line will be OP, right, which is the segment, the ray from O to P. Right. So essentially, what we have is the green line will be the initial ray, right, initial side of the angle, and then the orange will be the terminal side, which is the one we want. So on the end, this point will have the polar coordinate of 2 and pi over 6. Now we actually have some names for polars. So let's just talk a little bit about that. All right, here we go. So in terms of polar, even though we do use the same origin, right? Yeah, this point is the origin. Now, in terms of polar, we also call that the pole. Right? So you can think about a pole that's sticking out of the origin, and then you can rotate the pole, right? Which will make the line or the ray that's attached to the pole rotate as well. And then by how much that rotate, that determines your theta, right? And then the length of the ray, that will be r, right? R here, right? And after you rotate the initial ray by a certain angle theta, on the tip of the ray after rotating, that point will have the coordinate of r theta. Okay, so that's the basic idea of polar coordinates. Now, there are a lot of fun things that we can do with polar coordinates. For example, what about, let's say I want to plot P of 2 and negative 11 pi over 6. Okay, so let's see. If we want to do that, it's very simple, right? They tell us what the initial ray is going to be, right? Initial ray will have the radius of 2, right? So it's going to be this long, right? And then we have to rotate this pink ray by negative 11 pi over 6. Negative 11 pi over 6 is negative 330, right? So if we rotate that, negative 330, we get about here, right? So that's negative 11 pi over 6. Right, so if we rotate that, you can think about it as the terminal side will be somewhere around here. Oops, that's a little too long. Right here, right? So this point will be P of 2 and negative 11 pi over 6. But think about this. Instead of rotating the pink ray by negative 11 pi over 6, why can't we just rotate it positively right here, right? And then if you subtract 2 pi, if you subtract 11 pi over 6 from 2 pi, you actually get pi over 6. So by taking the initial rate and rotating it by negative 11 pi over 6 and by pi over 6, you actually get to the same point, right? Because the terminal side of these two angles are the same, right? So in this case, we can say that the polar coordinates of 2 and negative 11 pi over 6 is actually equal to the polar coordinates of 2 and pi over 6, right? Because it doesn't matter whether you're rotating counterclockwise or clockwise. If you land on the same point, then they have the same coordinates, right? It's just different way of representing it, right? And we did not have this in the regular Cartesian coordinates, right? With the xy plane, if uh, we only can get to the same point if both x value and y value are the same, but not in this case, right? Polar coordinates, we can represent one point with many different ways, right? And let's say if we have p of -4 and 0. Okay? So 0 means we are not rotating anything, right? If the angle is 0. Okay, here we go. So -4 for radius. Now we know to the right is positive, so negative will be -1, 2, 3, and 4, right? So we are actually working with this line right here. Okay? So you can think about it as stretching it to the right. Right? We have this whole line, but the part that we actually care is to the left hand side. Now 0 means we are not rotating this ray, right? So p -4 0 will be right here. Okay. Whereas p of positive 4 and 0 will be right here. Okay, because we're now rotating and we're taking a positive radius of 4. Right, so negative radius is just going to tell you that we are actually pointing in a different direction. Okay. All right, so let's do one example. Find all the polar coordinates of the point P of 2 and pi over 6. Now let's we actually graph that. Let's copy that over. This is the graph we're looking at, right? Okay, so we want to figure out how many ways can we get to that same point, right? So first, we know we can get to there by rotating pi over 6, and we can also rotate a full rotation before hitting pi over 6. So we can do p of 2 of pi over 6 plus 2 pi, right? That will give us the same point, right? Because 2 pi is a full rotation, and then we can get to pi over 6 by rotating an extra pi over 6. And we can do 2 full rotation, right? Plus 4 pi. And then we'll get to the same point as well. And actually, you can do however any rotations you want to get to that same point, p of 2 and pi over 6. Now, we can also do the other direction, rotating in the other direction like that, right? Which we saw earlier, which will be 2 and a -11 pi over 6. Or I can do a negative full rotation and then another -11 pi over 6, right? So what we have is p of 2 for pi over 6 minus 2 pi, which will be the same thing as that. Or we can do p of 2 and pi over 6 minus 4 pi, and we'll get to the same place as well, right? Which is what we have here. And minus 4 pi, minus 8 pi, and so on, right? So basically, what we can do is we can, as long as our radius is 2, we can do any combination of rotation of 2 and pi, right? As long as the 2 and pi will represent either positive or negative full rotation. And as long as we have pi over 6 after that, we will get to the same point. Okay. Now, another way to do this is a little different. Okay. I'm going to draw a new XY plane. Okay. So our goal is to hit this point somewhere around here, right? And what we're going to do now is we're going to think about this in a negative radius idea, right? So instead of take a positive radius of 2, I'm going to take a negative 2 radius. Okay. And how do I rotate to this point? Right? So I can rotate this way, right? Or I can rotate in the counterclockwise direction this way to get to that. And our goal is to figure out, right, what these angles are, right? So we know that this is pi over 6, right? And if you look at the blue one, which is going to be a positive rotation, right? That's positive rotation because it's counterclockwise. To rotate from the initial side of this orange segment to the terminal side, we have to rotate a total of pi and then pi over 6. Okay, so this segment here is pi. Right? So if we rotate pi plus pi over 6, which is 7 pi over 6, with a negative radius, we will get to that point, right? So this point will have the polar coordinates of negative 2 and 7 pi over 6. Okay? So very interesting, right? There are many different ways we can represent the same angle, or the same coordinates on the XY plane. Or another way you can do that is you can do the negative rotation, which is what we have here, right? That rotation is going to be pi minus pi over 6, which is 5 pi over 6. But it's in the clockwise rotation, so that will have the angle of negative 5 pi over 6. Now, it actually doesn't matter which one you pick. You are representing the same thing, right? So let's say I'm going to take the positive rotation, which is 7 pi over 6. So we can represent that point as negative 2, 7 pi over 6, plus or minus 2m pi. And again, the 2m pi will include all the possible full rotation that you want to do before hitting that point, before hitting 7 pi over 6. Or you can do negative 2 and negative 5 pi over 6 plus or minus 2m pi, which will get you to the same place, right? Just depending on whether you prefer the clockwise rotation, which is in green, or the counterclockwise rotation, which is in dark blue. Okay, but overall they are the same thing. Okay. All right. Now next we're going to look at a function in polar coordinates. Let's say r is equal to 1. Okay. So r is equal to 1. That tells us the ray is going to have a distance of 1. And it doesn't tell us about theta. That means just like in Cartesian coordinates, that theta can be anything, right? Now, in this case, what we have is this, right? We have the plane, and then we have r is equal to 1 right here, right? And then since theta can be anything, right, it can also be this one, right? Or that one, or that one, or that one, or that one, right? Maybe a little longer. Okay, so actually what we have when we have r is equal to some constant, it represents a circle of that radius, right? And basically what it's telling us is that, okay, radius is equal to 1. All right, so if we have radius is equal to 1, exactly what we have. We just have a circle with radius 1, right? And when you have a function that is r equals to 1, that actually represents a circle with a radius 1, right? And if it's 2, then it's a radius 2, circle with radius 2. Right, so let's write it down. R is equal to a represents a circle with radius a. Okay. So very nice, and I think it's intuitive as well. Right? So let's look at something that's a little more fun. All right, so let's look at example 2. A circle or a line can have more than one polar equation. For example, part A, r equal to 1 and r equal to -1 are equations for a circle of radius 1, center at 0. Right? It doesn't matter if it's +1 or -1. If it doesn't specify the angle theta or the rotation, it means you can rotate any however many rotations you want, and then at the end you will just get a circle with radius 1. Right? Doesn't matter if it's 1 or -1, but when you graph out the circle, the radius is always positive, which is a 1. Right? So r equal to 1 and r equal to -1 are will actually give you the same graph, right? The same circle. And part B, pi over 6, 7 pi over 6, and -5/6 are equations for the line in figure 11.23, which is this one, what we have here, right? So doesn't matter how you rotate, right? If you rotate pi over 6, 7 pi over 6, or -5 pi over 6, you actually will get to the same line, right? And notice that in this case, this function does not specify what the radius is, right? So the radius can be anything that goes through the pole, right? So let's say you rotate by pi over 6, right? And then you draw a line that goes through the origin, you get that, right? Or you can rotate 7 pi over 6, right? 7 pi over 6 will get you here, right? 7 pi over 6. And then since it doesn't specify the radius again, you can just draw a straight line that goes to the origin, and that gives you the same line, right? And the last one, -5 pi over 6, right? You can do the same thing. Rotate from the initial side by -5 pi over 6, which will get you here. And then again, you do the same thing. You draw a straight line that goes through this point and the origin, right? And then you get this line. Right? So 3 of the same lines, but with different equation, right? So to represent a straight line in polar coordinates, all we need to figure out is what theta is, right? And let's do a quick example to elaborate on that, right? Very simple. Y equals to x, right? Y equals to x is just a straight line that goes through the origin, right? Like this. Right? Y equals to x. Right? Maybe not the best one I have drawn. Something like that. Okay. Y equals to x. Okay. And then we know that if we draw a right triangle like that, let's say this point is 1, 1, right? That was 1 and 1. That's a isosceles triangle, right? And we know that this angle is going to be 45 degrees, or pi over 4. Right? So we can actually represent this line, y equals to x, in polar equation. That is the same thing as theta equals to pi over 4. Right? Or if you prefer to be a little fancier, right? You can do a negative rotation, which will be -3 pi over 4. Right? So we can also represent this as theta equal to -3 pi over 4. Right? Or if you want, you can also do the third one, which is rotate to this point right here, right? Which will give you the same line, right? And that will be 5 pi over 4. All right, so theta equals to 5 pi over 4. And all these 3 equations in polar form represents the same line, y equals to x. Right? Very interesting. We have many different ways of representing the same line using polar coordinates. And I know that might be a little tedious, but as we move on to the next few sections, we will look into more details with polar equations, and that will be much more interesting. Now we want to talk about how we can relate our regular Cartesian coordinates with polar coordinates. Now, for those of you who still remember trigonometry, this will ring some bell with you. All right. So here, x is equal to r times cosine theta, and y is r sine theta. And r squared is x squared plus y squared, with tangent theta is equal to y over x. So let's take a look on the xy plane, and hopefully this will make much more sense. All right, and let's say we have oops, some point r theta, xy, and in polar will be r theta. Right, so what we know is xy means um, the horizontal distance is x and the vertical distance is y, right? And then we have the r here. Now that's a right triangle, and by Pythagorean theorem, we can show that r squared is actually equal to x squared plus y squared, right? The Pythagorean theorem. Okay. Now let's look at the relationship of x, right? This is theta, right? Our reference angle. So we know cosine theta is adjacent over hypotenuse, which is, let me write it down, adjacent over hypotenuse, which is equal to x over r. And to we multiply by r to the other side, we get x is equal to r cosine. Right? And similar for y. Right? We know sine theta is opposite over hypotenuse. And in that case, it's going to be y over r. And then multiply r again. Y is equal to r sine theta. Okay? And that's how we get these, the first two. Right? And the last, to connect x and y together, we can use the third trig function, which is tangent theta, that is opposite over adjacent, right? And that will just be y over x. Okay, so all these are very straightforward. You know, we got this from trigonometry, and we can use that to relate between polar coordinates and Cartesian coordinates, right? And it's going to be very fun. Right, let's take a look at a few examples. All right, so here are some plane curves expressed in both polar and Cartesian, right? So let's look at the first one. R cosine theta is equal to 2. Now we know R cosine is just x, right? So really in Cartesian, it would just be x equal to 2. Now some of them are actually pretty straightforward, but if you look at the last one, right? R is equal to 1 minus cosine. In polar form, that looks very easy, right? 1 minus cosine theta. That's pretty easy to graph, as we will see in the next section. But if we translate it into Cartesian equation, right, that looks very crazy, right? We have polynomial with two variables, and we have basically no idea how to start graphing this, right? So depends on the type of graph you're working with, right? Maybe a Cartesian will be easier, maybe polar will be easier. So let's do a few practice on how we can convert between Cartesian and polar. All right, our first example is x squared plus parentheses y minus 3 quantity square is equal to 9. Now, for those of you who are so familiar with circle, that is actually an equation of circle, right, with a center 0, 3. All right, so let's try to see if we can convert that to a polar equation. All right, so first thing, right, let's write out the translation we're going to use, right? X is equal to r cosine and y is equal to r sine. And very simple, very straightforward. You are just going to plug that in, right? When there is x, you replace it with r cosine. When there is y, you replace it with r sine. Right? Let's see what we have. Okay. So I have r cosine theta quantity square plus r sine theta minus 3 quantity square is equal to 9. And let's expand that. I get r squared cosine square plus it's a binomial square, so I'll be r squared sine square minus 6 r sine theta plus 9 is equal to 9. All right, and let's try to clean this up a little bit. First, I'm going to subtract the 9 to the right, so we have 0. All right, and factoring out the r square first for the first two terms. All right, I have r square parentheses cosine square plus sine square, which will be nice, right? Because that's just one minus 6r sine theta is equal to 0. Right, and sine square plus cosine square, that whole thing just goes to 1. Right? So we have r square minus 6r sine theta is equal to 0. Right? And if we try to solve this, we can factor in r and get r minus 6 sine is equal to 0. Right? So r is 0. So basically we get two possibilities, right? R is equal to 0 or r minus 6 sine is 0. Now r is 0 is just a point, right? On the pole or on the origin, right? So we're not going to worry about that. And to simplify this, right? R minus 6 sine theta is equal to 0 will be our circle, or we can write that as r is equal to 6 sine theta, right, in polar form. Right? And that is our final answer, which represents the same circle that looks like this. Okay. Right? It's a circle with radius 3, center at 0, 3. Or we can represent it as r equals to 6 sine theta. Right? They're both pretty nice form. And it's just different ways of representing it. All right, so for example 5, we went from Cartesian to polar. Now let's look at example 6. We're given polar equations and we want to convert that to Cartesian equations. Right? So let's start with the first one, which is very straightforward. All right, arc cosine theta is equal to -4. Now arc cosine is just x, right? So that's just x equal to -4. Done. Very nice. It's a vertical line that goes through x equal to -4. All right, let's look at the second one. We have r squared is equal to 4r cosine theta. Okay. All right, so let's take a look. R squared from the Pythagorean part, we know that it's equal to x squared plus y squared. And that's what we're going to replace r squared with. Right, so x squared plus y squared on the left-hand side. And on the right-hand side, we have 4r cosine. And we know that r cosine is just x, right? So that's just 4x. Okay. Oh, of course, you can leave it that way, but we really have no nice idea of what this is, right? So let's do a little extra work. I'm going to subtract the 4x to the right. Right? So I have x squared minus 4x plus y squared is equal to 0. And what I'm going to do next is I'm going to complete the square on this part. Okay. So to complete the square, we need to add the square of half of b, right? Minus 4x plus y square is equal to 0. Right, so in order to complete the square, we need to add half of -4, which is -2, and -2 squared is 4. All right, so add a 4. And to do that, we also need to add a 4 on the right. Right, and by doing that, we can factor this part into x minus 2 square. Okay, and then plus y square is equal to 4. All right, now when we have this equation, we can easily tell what this is, right? It's a circle, right? X minus a squared plus y squared is equal to r squared, right? So it's a circle with radius equal to 2 and center at 2, 0. Okay? And that's much nicer, right? Comparing to what we were seeing here. R squared equals to 4r cosine theta, right? We have no idea what this equation represents just by looking at the equation without graphing it, right? But when we convert that to Cartesian, since we have more knowledge about Cartesian coordinates at this point, we know that this equation represents a circle, right? And that's something pretty fascinating, I would say. Okay, let's look at part C. Right? Let me copy it down here. Part C is R is equal to 4 over 2 cosine theta minus sine theta. All right. So we have R on the left, and then in the denominator here, we just have cosine and sine. So that's really a little hard to work with uh, like this. So what we're going to do is I'm going to multiply the denominator to the left-hand side, right? So I have R times 2 cosine theta minus sine theta is equal to 4, right? And when we distribute the R, we get 2R cosine theta minus R sine theta. And hopefully you guys can see why we want to multiply this to the left-hand side, right? Because we have the nice form of R cosine, which is X, and R sine, which is Y, right? And to simplify this, we just get 2x minus y is equal to 4. Right? And by moving some things around, we get a y is equal to 2x minus 4, which is a nice linear equation, right? Okay. So here's another example that in polar, it might look really crazy, but when we convert that to Cartesian, it's actually something we are very familiar with. It's a linear equation with slope equal to 2 and y-intercept equal to -4. Okay? So in this section, a lot of the practice homework problems are going to be like this, right? You either want to convert from polar to Cartesian or from Cartesian to polar. Of course, some question to help you warm up, like identifying polar coordinates, which polar coordinates give you the same thing, right? And things like that. There are actually a lot of cool animations on YouTube um, to help you understand what polar coordinate is. Feel free to check those out. And yeah, that will be all for today. Thank you guys very much, and I'll see you next time.